ClearCove Systems has been awarded funding from NYSERDA to perform a demonstration project of its Enhanced Primary Treatment, or EPT technology, at the Ithaca Area Wastewater Treatment Facility. The purpose of this demonstration is to validate the benefits of installing the EPT at full scale. These benefits include aeration energy savings, increased biogas generation, relative capacity increase of the anaerobic digesters, improved sludge processing, and improved plant chemical costs and usage. In this video, we will explain the operation of the ClearCove EPT in the mini digester pilot. The EPT has been placed outside the plant's influent building. The pilot pumps raw sewage at a rate of 80 gallons per minute from the influent channel prior to any treatment or chemical addition. As the wastewater enters the pilot, it is dosed with coagulant and polymer in the influent piping. After the chemical addition, the flow is split and sent to the influent feed systems at either end of the tank. The wastewater first enters the influent feed system through the grip box. The rise rate of the grip box is 0.12 feet per second, allowing the densest and heaviest solids to settle out here. After filling the grip box, the wastewater then fills the rest of the influent feed chamber. As it fills, the surface area of the trough increases, which causes the vertical rise rate to decrease, even further allowing for medium and density solids to settle. The flow path has several 90-degree turns to reduce momentum, directional velocities, and dissipate the pumping energy. After the wastewater has filled the influent feed system, it flows over the weirs on opposite ends of the tank and into the main chamber of the EPT. The weir is angled at 70 degrees so that the water does not waterfall into the tank, but instead coheres to the face of the weir. This is done so that the filling of the wastewater does not disturb the solids which have already begun to settle. The wastewater flows from both sides of the tank and collides in the center, dissipating its energy and allowing for settling to begin to occur as the tank fills. Once the tank is full, a 35-minute settling period begins. During this time, the organics and solids settle to the bottom of the tank. In a full-scale application, this settling period would be dependent on flow rate into the facility. During high flow events, such as storms, the settling period would be short. After every fourth settling period, an actuated valve opens and draws the sludge from the bottom of the EPT and into a 900-gallon holding tank. This is done to prevent the sludge blanket at the bottom of the EPT from getting too high, as it could reduce the BOD removal efficiency of the system. After the settling period and sludge draw-off, the decant cycle begins. A 50-micron stainless steel screen box is lowered into the low solids, low BOD supernatant at the top of the tank. The wastewater flows through the screen and down a central effluent hose. At full scale, this effluent will move on to secondary treatment. However, for this pilot, the effluent is sent back to the head of the plant. The effluent flow rate is controlled and is a function of the surface area of screen that is submerged in the wastewater. The bubbling seen around the face of the screen is from an air scour used to deflect floating solids and fibers in the wastewater from coming in contact with the screen. At full scale, there will always be at least 2 EPT tanks. While one tank is filling and settling, the other tank is decanting, allowing for a constant flow of wastewater in and out of the system. The ClearCove EPT is a fully automated system. Through the EPT SCADA system, modes of operation and operational parameters can be adjusted. A few examples include chemical dosing, influent pump rate, settle time, and effluent flow rate. The EPT's SCADA system also allows for real-time monitoring of the organic load in and out of the pilot unit through the use of ultraviolet absorption spectrometers, or UVAS probes. In addition, the SCADA system has a historian which records all aspects of the pilot's operation into a cloud-based report. The sludge drawn off from the EPT pilot is sent to a 900-gallon holding tank prior to it being processed. From the 900-gallon holding tank, the sludge is sent to the Sludge Classifying Press, or SCP. The SCP is a technology which removes the larger inorganics such as plastics from the sludge. The SCP also squeezes the larger encased organics, allowing for their inner organic content to be added to the sludge. From the SCP, the sludge is pumped to a 300-gallon thickening tank. The sludge is left in the thickening tank for approximately an hour, at which point is removed at about 2% solids and sent to the mini digesters. To study the energy production side of the project, 4 350-gallon custom hopper-bottom mini digesters were installed in the digester room of the Ithaca plant. The digesters were designed to operate with 100 gallons of working volume. Each digester has a dedicated feed tank which feeds its specific sludge. Digester 1 is fed thickened sludge, which is a combination of primary sludge from the plant's primary clarifiers and secondary sludge from the plant's activated sludge process. This is the same sludge that Ithaca feeds its full-scale digester. Digester 1 is also fed at the same rate as Ithaca's full-scale digester, which is 50 pounds per day of volatile solids per 1,000 cubic feet of digester volume. Digester 2 is fed only primary sludge from Ithaca's primary clarifiers. Digester 2 is also fed sludge at the same rate as Ithaca's full-scale digester. Digester 3 is fed enhanced primary sludge from the EPT pilot at the same rate as Ithaca's full-scale digester. Digester 4 is fed enhanced primary sludge from the EPT pilot at double the loading rate as Ithaca's full-scale digester, at 100 pounds per day of volatile solids per 1,000 cubic feet of digester volume. Digester 4 is fed at double the rate to test the hypothesis that enhanced primary sludge is more rapidly biodegradable. Each digester has 2 dedicated pumps, one for heating and mixing, and the other for feeding. In order to heat and mix the digesters, sludge is pumped from the bottom of the digester and through a heat exchanger, which keeps the temperature of the sludge between 95 and 98 degrees. The sludge is then pumped back over to the digester and injected into the tank through 4 internal nozzles, thus providing the mixing for the reactor. To feed the digester, sludge is pumped from the digester's dedicated feed tank and through a recirculation loop. In each recirculation loop is a solenoid valve which opens and closes based on a timer to redirect feed to the top of the digester. The timing of the solenoid valve is adjusted to deliver the target pounds of volatile solids per day to each digester. Biogas from the mini digesters is vented through flow meters outside of the digester room. The measurements of the flow meters, as well as the temperature probes for each of the digesters, is continuously recorded on a PLC. Biochemical methane potential, or BMP testing, is being performed in parallel with the mini digesters using the AMPTS-2 system by bioprocess controls. The same sludge types as the mini digesters are tested using the BMP reactors to provide supplemental and supporting gas data. The BMP reactors all sit in an incubator bath at 98 degrees Fahrenheit. The gas generated in the reactors is then scrubbed for CO2 prior to entering the methane measurement device. The methane measurement device then records the gas flow from each reactor to a software platform provided by Bioprocess Controls to a dedicated computer, allowing for real-time monitoring of the reactor's performance.